Hi there, welcome to a video about isotopes. This is really a recap from your first year of chemistry. The only thing that might be tricky is kind of towards the end, so let me help you out with isotopes and how the recap would look like. I got my screen down here, so I'm going to be looking down a lot if you're watching me in the video. Starting with atomic symbols and isotopes. So as a quick recap, the atom we know has really two big parts. One, it's got the nucleus in the center, and inside the nucleus we know we have protons and neutrons. The nucleus is positively charged because it has protons, which are positively charged, and neutrons, which are neutral. Now, along the outside is mostly empty space, but we do have a few very small electrons that fly around. So this would be one example of a carbon atom, or you could say this is one carbon isotope. The word atom and isotope are kind of interchangeable. They're a little bit different though. So looking more at the carbon, if we looked at your periodic table, you would see a box for carbon that looks something like this. This top number here is our atomic number. This number down here is what would be your mass number, or better off saying, because this is the 12.011, a better way to say it would be your atomic mass. Mass number is actually a little bit different, and it's always going to be a whole number. Atomic mass is going to be an average. So to be more clear, we could call this an average atomic mass, because there is no atom out there in the world of carbon that has a mass of 12.011. It doesn't exist. The mass of any atom is going to be more of a whole number sort of thing. Well, not exactly, but pretty close. So then you've got the symbol and you got the name. So that's all the parts to it. Now what the atomic number can tell you is actually that's the number of protons that you have. In an atom, atoms are neutrally charged, so that also tells you the number of electrons. But down here, this number down here is kind of giving an inkling into what kind of atom it actually is. In other words, the number of neutrons it has. So there are actually a couple different types of carbon. These are the three types. There's carbon 12, carbon 13, and carbon 14. Now notice on the average atomic mass, none of them is 12, 13, or 14. The average is 12.011. That's because most of the carbons in the world are carbon 12. Most of the carbons in the world look like this atom that we started with, where it has 6 protons, 6 electrons, and 6 neutrons. But it can actually change. Sometimes you've got a carbon, this is carbon 13 that I'm going to make, and this red one here is our carbon 12. If you had carbon 13, that would mean it has 6 electrons, 6 protons. You're not going to change the number of protons. If you do, you change the type of element it is, and it will have 7 neutrons. 6 plus 7 equals 13. 6 plus 6 is going to equal 12. So when I take this atom and I want to suddenly make it into a carbon 13, I've got to add a white circle here for an extra neutron. An isotope is the same number of protons, but a different number of neutrons. It's still the same atom. In other words, it's still carbon, it just has a different number of neutrons. So going back down here, so I can see that carbon 12, it has 6 protons and 6 electrons and 6 neutrons. Carbon 13, though, will have 6 protons, 6 electrons, and 7 neutrons. Carbon 14, 6 protons, 6 electrons, and 8 neutrons. So we can see the only thing that's different is my number of neutrons. We can also show that by doing isotopic notation, which is this bottom part. You can see the bottom number is always going to be your atomic number, but the top number is going to be your mass number, and it changes. Which is kind of nice because then you can do 12 minus 6 and you get 6. That's the number of neutrons. Kind of makes for quick math doing it this way. All right. You might have to fill in a chart. On the AP test, not so much, but this chart will give you good type of practice. So let me take it step by step here. If I have carbon 12, this 12 is my mass number, or my atomic number. No, I'm sorry, atomic mass. Here we go. My atomic number is going to be the number on the periodic table on the top part. That's the big numbers. For carbon, it's 6. It's number 6 on the periodic table. And that 6 tells me the number of protons, tells me the number of electrons, and the mass number gets me an inkling into the number of neutrons. My mass number is the number of protons plus the number of neutrons. In this case, that happens to be 12. And if I know my protons is 6, my neutrons has to be 6 also. My atomic symbol then would be the 12 and the 6 on the bottom. We'll take it with nitrogen. This 7 here tells me my atomic number, which is the number of protons and the number of electrons. They've got to equal. This top number right here is my atomic mass, or mass number. That's 15. And if I wanted to find the number of neutrons, 15 minus 7 is going to get me my 8. 8 neutrons in this nitrogen. nitrogen 15. Sorry, I shouldn't have 2 lines there. All right, taking a look at the last example on the bottom here. 19 is the number of protons. Well, that tells me how many electrons I have. It also tells me my atomic number. It also tells me what element I have. If I look for number 19 on the periodic table, it's K for potassium. And that 19 goes on the bottom. In order to find my atomic mass or a mass number, I'm going to take this 20 plus this 19 to get me 39. This is potassium 39. Now, there's my answers right there. So when we get that periodic table number, as I said with the carbon at the top, 12.011, a carbon doesn't actually have that. No carbon has that mass. Let's look at chlorine. Chlorine on the periodic table, if you look for it in the periodic table, it's right over here at number 17. It has a mass of 35.45. Chlorine, its mass is 35.45. You're never going to find something with a mass of 35.45, but what that means is most of the chlorines in the world is chlorine 35. It's very close to that number. But there are a few chlorines in the world that are chlorine maybe 37. And because of that, we can look at these two and we can average them. In other words, you take all the chlorines in all the world and average their atomic mass. It'll be closest to 35 because most of the chlorines in the world is chlorine 35. But there happen to be some that are 37, which makes the mass not 35, but a little bit greater than that. You're going to be looking at a lot of these type of charts. That's more of an AP thing to look at. So you want to be able to read the chart quickly by looking at the y-axis, relative abundance, that tells me how much there is, and looking at the x-axis. Now this part might be tricky to you. This is mass to charge, and we're going to talk about that later when we talk about mass spec. But what that's really looking at is the mass number of things, because the charge is always a +1. So it's really looking at mass. All right, let's try a little bit trickier problem. You may or may not have done this in your first year chemistry. So copper is made of 2 isotopes. This one here, that's isotope number 1, and this one right here is isotope number 2. And so I'm trying to find what's the percent abundance of each isotope. Now this is an average. In this case, it's a weighted average. I can't just add these two values and divide by 2. That assumes that they're both 50%. There's 50% of them in the world, but that's not true. So what I'm going to do is set up a problem like this, where I'm going to take isotope 1 here and do my math for this part there. Here's where isotope 2 is going to go. And if I add isotope 3, I'd add another, another, and another, depending on how many isotopes I have. And that'll get me to the average. In other words, the average according to the periodic table. If I look for copper, boom, 63.55. 63.55. So that would be the weighted average. So that's going to be this part over here. And the weighted average is going to be composed of the 2 weighted parts. Now the first one has a mass of 62.9296, and the other one has a mass of 64.9278. What I don't know is the percentages for each. So I'm going to call this percentage X, because I'm going to take this percentage times the mass, plus this percentage times the mass. Now again, I don't know this percentage. I could call it Y, but that just makes my life tricky. So what I'm going to say is 1 minus X. Because I know whatever X is, it'll be a percentage, and I'll have it in decimal form. So let's say it's 36%. Well then, my X will come out as 0.36. That would mean 100 minus X would get me whatever its percentage is. In this case, if it was 36, that would be 64%. Or in other words, 0.64. So what I'm going to do by doing 1 minus X is taking, okay, the whole is 1, and the part would be maybe the 64% or the 36%. And I'm going to try and find out what that is. So this is the math I need to solve in my calculator. I did it for you, Blue. Boop. When I do the math, I find that X is this one here. And so I get a percentage of both of those to be 69% and 30.85%. We're going to be looking at a few AP questions on the Google form, but here's another AP question that's in the multiple choice. Which of the following represents a pair of isotopes? Now I can see in the table I'm looking at atomic number and mass number. I know that isotopes always have the same atomic number. Same number? Nope, doesn't work. Looking for the same number? Nope, doesn't work. Looking for the same number? Nope, doesn't work. Looking for the same number? Got it. This one also doesn't work. So I'm going to say to myself, D is the answer. And if I look better at it, I can say yes. Same number of protons, but different number of neutrons. Those are 2 isotopes of each other. All right, send me a question if you have any. I hope that helped.